Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to describe for you what electric field lines are. Now first of all, I'm going to talk about what they are in general, and then we'll talk about how they're drawn and interpreted. So what they are is they're lines, and they don't have to be straight, that help to visualize and describe the electric field around some sort of charge distribution. Now there's two very important rules for electric field lines, and I've written them up here. Rule number one, the magnitude of the electric field is directly proportional to the number of lines per unit volume. Now, you'll see over here I put in parentheses area. I'll describe why I did that a little bit later in the video. But for now, the electric field is directly proportional to the number of lines per unit of volume. What that means is in your picture where the lines are very close together, it means that the electric field is strong. Rule number two, electric fields are tangent to the field lines at all points. Right? So what I'm going to do now is I'm going to go through a picture here of drawing electric field lines around a positively charged particle. Now I'm going to start by drawing just some electric field vectors around this particle. So I'm going to start right here, and I'm going to draw some electric field vectors. Now the electric field at this point in space would point maybe to the right. If you're not sure where I'm getting that from, review my video on electric fields and how to determine their directions. Remember, electric fields always point away from positive charges. Now, if I were to come equal distance here to the left, there would be another electric field vector of the same magnitude. Again, if I go equal distance, there's no reason to think the field here is going to vary compared to the one over here. Now, I'm going to do some on the vertical here. If I come up, same distance away, there's an electric field vector that points this way. If I come down, again, same distance. Here's some more electric field vectors. I'm going to go ahead and do some more here. And again, imagine I go same distance away, field would point this way, same magnitude, right? Same distance, field would point outward, same magnitude. So what I have now is I have a series of electric field vectors. I guess I'll do one more pair. Again, if I go same distance, field is going to be this way, same magnitude as all the others, same distance, same magnitude. Now I did this by eyeball, so it's likely not perfect, but the idea is as long as these points along here, are all the same distance to this charge, then these electric field vectors should be the same. Now, had this been negatively charged, these would all point inward. Now, if I draw like one more here, I go back to this line here. If I go about twice as far, the electric field would be about 1/4 as long. Now, if you're wondering where I'm getting that from, just go back and review my video about electric fields due to point charges and how they're calculated. And if I go even further out, the electric field would be quite a bit smaller. The further out we get, the weaker the field. Now, these are electric field vectors. What do the lines look like? I'm going to go ahead and draw them in green. I'm going to offset that just a tad here. So the electric field lines are lines that, in this example, they would radiate outward. And again, they don't have to be lining directly up with these electric fields. You can draw these lines pretty well anywhere. And electric field lines themselves are not vector quantities, but they do in a sense have a direction. They can be away or towards the charge. Because this is positively charged, the electric field lines point away. So now what we have is we've got this series of lines in space. Now, let's talk about how these rules apply to these lines. You notice that if I were to do something like this, like draw kind of a little area there, you notice there's 1, 2, 3 lines there. But if I come out further and I draw the same area, well, now only one line goes through it. So in the picture, because the lines are tighter spaced here, it means the electric field's quite a bit stronger than out here. So again, that's roughly what this rule means. The electric field is directly proportional to the number of lines per unit volume. Now, the reason I put kind of area here, so in the picture, where these things are closer together like this, area-wise, that means that the field is stronger in that region. Now, it just looks like an area. Again, it's really a volume. You got to picture like a three-dimensional volume in space here, where the more lines go through any given volume, that means the electric field is quite a bit stronger. Now, you'll notice if I follow one of these lines out, like if I come way out here, the electric field is got to be to the right because of this rule. Electric fields are tangent to the field lines, and it has to be relatively weak because there's just this one line here, and you got to way out here until there's more of them, until you hit another one. So in close to this charge, the lines are tightly spaced. It means stronger field. We get away from the charge, like out in this region, the lines are much more sparse. It means weak field. And the electric field is tangent to the field line at all points in space. So I'm going to pause this and again make up some examples here to demonstrate these rules. So give me a moment. Okay, I'm back, and let me describe a little bit here about what I've drawn. So what I've drawn is, imagine some sort of region in space, and these green lines are electric field lines that are meant to represent electric fields in this region in space. Now, don't worry about what type of charge distribution would get us this type of field. That's not important. The purpose of this is to learn a little bit about how to interpret the field lines. Now, I picked a couple different points here, A, B, and C. You'll notice that C isn't actually on a field line. That's perfectly fine. When you pick points in space, they don't have to be on the field lines. I picked a couple that were and one that wasn't. And what I'm going to try to do here is draw electric field vectors, and I think I'll draw those in red, at all these different points. And I'm going to start with the point where I think the electric field is strongest. Now, you'll notice that if I draw like a little almost spherical surface here, I got three field lines basically going through there. Here if I kind of stretch it, maybe one, and again here maybe one. The important thing here is notice that here the field lines are very tight together. So the number of field lines per unit volume is a larger number here than either of these two spots. So the strongest electric field is going to be at point B. Field lines are tangent to the electric field vectors, or I should say the electric field vectors are tangent to the field lines at all points. So tangent to that point right there might look something like this. So the electric field at that point in space is relatively strong. So I'd use a relatively long vector to describe it. And there it is. Tangent to the field line, relatively strong field because there's, I got like 4 lines in this region here compared to like, a lot less here and here. Now the length of this vector, it was fairly arbitrary, but knowing that this is the longest electric field vector on the page, I tried to draw it relatively long. The rest of them will be shorter. Now when we compare points B and C, you notice here there's quite a bit of distance between A and the next field line this way, A and the next field line this way, and it's really a three-dimensional thing. You almost have to think about it kind of coming out of the page as well. C, you don't have to go as far to hit these other field lines. So the next strongest electric field is definitely at C. Now, I don't have a field line right at C to be tangent to perfectly, but I can kind of infer the direction. It's probably somewhere between these two. So tangent here would be like this way. Tangent here is kind of down and right. So the electric field vector at C is probably something like this. Its length, well, it's hard to say exactly, but it's quite a bit less than this for sure. So I'm going to go ahead and drop it in length quite a bit. So there's an electric field vector at point C. A, probably the weakest field of the three. And because A is right on a field line, I can get the tangent pretty easily. So this is going to be kind of a short electric field vector. So again, you'll notice that the electric field vectors are tangent to the field lines at all points. And also notice that where the field lines are close together, that means strong field. And then the field lines are further apart, a little bit weaker field. And here the field lines are the furthest apart, so an even weaker field. So that's a little bit about how to interpret the electric field lines. Again, the video's closing in on 10 minutes, so I think I'll just kind of end it there. Again, important things to remember. The magnitude of the electric field, which means the electric field strength, is directly proportional to the number of lines per volume. It kind of looks like per area on the page again, because on this two-dimensional page, it kind of looks like an area problem, but it really is per volume. And two, electric field vectors are always tangent to the field lines. I hope this video helps describe these concepts. Have a great day.